So, thanks Nick, good morning. Well, the aim of my talk is to convince you all that even if you live in an urban, light polluted area, you can still enjoy the pleasures of comet imaging. So, let's see if this works. Oh yeah, there you go. Right, so comet imaging in Southend. Well, just so everyone's clear, Southend is not the most southerly tip of a faraway tropical island. It is actually a rather boring but busy conurbation on the Thames estuary in Essex, 36 miles east of London's Piccadilly Circus. So it's probably not the place that you would associate with comet imaging. But Southend-on-Sea is where I live, and it's the place I've chosen to set up my observatory. And here's my observatory location, just marked on a map, showing the surrounding levels of light pollution. And red on the map and darker colours are seriously light polluted, so not good. And this is what my sky looks like at about 1:30 in the morning, when the sky's got about as dark and as good as it's going to get, and that's probably not good either. Now, I could have chosen to do my imaging remotely, say using the iTelescope network, or I could pack all my gear into the car and go off somewhere where the observing conditions are much more favourable. But I decided if I was going to use my equipment frequently and do a bit of observing in the middle of the night, that my equipment had to be somewhere that was quick and convenient to use. So my back garden seemed like the logical location. And just to prove that it is quick and convenient to use, I recently timed my observatory setup process. And from unlocking the observatory door to the start of my first comet image took me 150 seconds, so no time at all. So I can make use of short clear spells in the weather, or I can get up at 3 AM in the morning to do a half-hour imaging session without too much fuss. Well, maybe a bit of fuss at 3 in the morning. But the observing conditions at my location, I think, are fairly typical of the observing conditions that are present in many sort of urban areas of the country, which is where, of course, the majority of the population live, and that includes us astronomers. Let's go forward again. So the main hurdle to me securing good quality comet images is quite obviously light pollution. But there are other disadvantages for imaging and observing from an urban area, like buildings obscuring your view of the sky, or smoke from next door's flipping wood burning stove. Or aircraft contrails, or vibrations from traffic on the busy road outside my house. Well, I can't do much about some of those problems without moving house, but I have adopted various techniques that at least improve the chances of me achieving the best possible images under these less than ideal conditions. And I'm going to go on and describe some of these techniques, because I think that the problems that I face are fairly typical of the problems that most comet imagers face. Unless, of course, you're Dennis, who lives in deepest, darkest Scotland, or Tony over there, who lives on top of a mountain in Spain. Mind you, Dennis has to put up with his own form of light pollution, which at this time of the year is the fact that the sun doesn't go very far below the northern horizon. And in the winter, I understand your sky gets full of coloured lights, which are all these aurorae. And Tony tells me that on occasion he gets cut off by 2 foot of snow in the winter on top of his mountain. So we've all got problems, but perhaps some of them are just nicer problems to have than others. So despite my bright night skies, I can, with my 300mm reflector and my entry-level CCD camera, record comets down to about 18th magnitude routinely. Sometimes fainter than that, as Nick said earlier, that I broke my record a couple of weeks ago with a 19th magnitude comet. And I can do it with sufficient quality to enable me to do astrometry on my images that I report to the MPC. And this is my image of Comet 2015 X8 Neowise, which I imaged a few days after it was discovered. It's 18th magnitude, and I did it with I did astrometry on this, and that astrometry was used by the MPC to refine the comet's orbital elements, and there's the MPC circular to prove it, and that's the sort of thing I quite enjoy doing. And with careful sky gradient removal, I try and do photometry on my images that I also try and report to the CEOBS World Database, and I must try and report it to Jonathan, because I think that hint was for me. But yes, I'm sure that the photometry bit will get talked about again today. So, I mustn't forget, of course, that I report my images to Dennis submit my images to Dennis for the section archive, and as Nick was saying, the archive's got thousands of images in it now, some are from me, and it's a very important image resource. So this is my image of 2015 V2 Johnson, taken in March this year, when it was fairly low in the eastern sky, and this comet was in the same area of sky that was shown on my previous picture showing my observatory, and I took it at exactly the same time. While this comet image was being taken, I went out and took a picture of the observatory. So I think it demonstrates what can be achieved in a fairly bright sky. Now, from my observatory, the view east is actually the least obstructed by buildings, but unfortunately it's the most light polluted, because about a mile away is London Southend airports and all the associated industrial area. But hopefully you agree that this is quite an acceptable image despite the conditions under which it was taken. And for comparison purposes, this is the same comet taken at a similar time with a slightly larger instrument, but from a properly dark desert location in Arizona. And it's by Gianluca Massi from the Tanagra Observatory, and it is better, but it's not a huge improvement, so I don't think I'm doing too bad. And just before Christmas 2015, Comet 2013 US 10 Catalina put on a good show, and this is my image again taken under similar poor sky conditions. So I think that people tend to get fixated about sky darkness, when of course that's just one factor that goes towards making a good image. Things like good steady atmosphere, good focus, good tracking, good firm mounting, they're all just as important, and of course all those factors can be achieved from a light polluted site just as well as from a dark site. So let's see what we'll go to the page here. So how do I attempt to alleviate some of the problems of light pollution? Well, I'm not suggesting that the techniques I'm going to describe are the only ways of getting good data, but they are the ones that seem to work for me. And I'm going to assume you've got some basic understanding of digital imaging and digital processing, so apologies to any non-imagers. Visual observers can have a quick nap now. I think that things fall into four categories, and they are site preparations, image acquisition considerations, post-acquisition calibration, and image cleanup techniques. And site preparations are common sense, really. I've tried to reduce all the local sources of light pollution where practical. I've made friends with my neighbours and tried to convince them that they don't need to illuminate their gardens all night, and that their pet cat can see where it's going in the night without a 500 watt floodlight to light its way. Hasn't always been successful, but there you go. And I've had reasonable responses from local businesses. The local Premier Inn, the Royal Bank of Scotland, and the local BMW showroom have all slightly adjusted their lighting habits after my pleas, and this is actually part of the grand title, the local retail motor village, I think it's called, and it's actually my main source of light pollution. It's about a quarter of a mile from the observatory, and they did actually take notice of me, and they adjusted all their lighting to aim it downwards, which I don't suppose they had to do. So my local authority, actually, I reminded them that their newly installed LED street lights are not supposed to be aimed halfway up into the sky, and that they are actually supposed to be aimed at the ground. And my local council actually went around the whole borough, and they readjusted the aim of all the lights after my reminder. So again, they do take notice. Yeah. And these have all been small changes, but they sort of have had a cumulative effect, which hopefully has improved a situation that would otherwise be worse. And personally, it makes me feel better to think I've tried to do something about it. So when I take my images, I try and wait, if at all possible, till the comet's culminated. So it's as high as possible in the sky, because obviously light pollution is the effects of light pollution is much worse near the horizon than it is overhead. And my sky darkens a bit after people have started to go to bed at about 11 o'clock. And my local LED street lights dim after midnight. So if at all possible, I try and wait till after midnight before I start my imaging. And contrary to what people might think, exposure lengths don't always need to be short just because of light pollution. What I try and do is to achieve the best possible compromise between a long exposure to get the best signal to noise ratio and an exposure short enough to avoid the comet trailing against the background stars. And my sort of default exposure for most comets under most circumstances is 120 seconds using my 300mm reflector working at f5.3. But the thing to do, or I think the thing to do, is to check the spread of pixel brightness levels using the histogram, which is an information window that's available in most image acquisition software packages and can be viewed on the back of most DSLR cameras. And the histogram is really just a graph showing the plots the intensity or how full the pixels are on the horizontal axis, and the numbers of pixels at those particular brightnesses on the vertical axis. And it's basically a distribution of all the shows a distribution of all the pixels at all the various intensity levels. So black in an image will be down this end, white at this end. So the stars and the central nucleus to the comet will be in the pixels up this end. The tail of the comet will be down here. And this great big spike of information, big spike of pixel numbers, is the light pollution in the background image, background sky. And I would suggest you choose an exposure that puts that big spike of information no more than about 25 to 33% of the way along the graph to the maximum. Now, if you're imaging near the horizon, obviously the sky will be much brighter. So the histogram is really important. It's really easy to get all the pixel values all bunched up at the white end like that, and that reduces the potential contrast range in your image, and potentially can saturate the stars and make the image look or make the stars look all bloated, not very clever. But when you're doing this, make sure that whatever exposure you choose, that not too many stars are saturated, and certainly that the comet, the centre of the comet's not saturated. Otherwise, you won't be able to do photometry. And now so I suppose the darker. Well, let me just do this bit first. So what what I do is to take lots of exposures, stack them together. I stack around 7 to 10 120 second exposures, or perhaps twice as many as that if I'm using 60 second exposures, and that seems to create reasonable detail in my images with a fairly smooth background. And the darker your sky, the fewer images you'll find you need to stack, because light pollution tends to manifest itself as sort of noise in the background image, which can really only be subdued with lots of data. I'll just pull the battery case off this. Let's put that down. I could use a light pollution rejection filter, but that would spoil the basic scientific value of the raw data, so it wouldn't be any good for subsequent photometry. And in any case, these days external lighting is fast changing to continuous spectrum white LED lights, so light pollution rejection filters will soon be a waste of time and will be useless, which is a bit of a shame. But one of the most important things you can do to any image taken under a light polluted sky is to properly calibrate it using good quality flat frames. And for those that don't know, a flat frame are images of a uniformly even light source, and they record the inherent sensitivity variations of the camera pixels together with shadows of dust in the optical train and the uneven illumination that is sort of inherent in the telescope design. And a flat frame typically looks like this. It's brighter in the middle than it is around the edges, and it's got the odd dark blob on it, which is shadows of dust in the optical train. And flat frames together with bias frames and dark frames are used to correct the raw images and remove all this uneven illumination and the other electronic artifacts. And this calibration process can be carried out using most image acquisition software packages. Now, if you don't calibrate your image and you contrast stretch it and stack it, that's what it looks like. Bit of a mess, really. There's a comet in the middle there, believe it or not. But the image will end up looking bright in the middle, dark around the edges, got a few blobs on it, dark blobs, and got a few light blobs, which are hot pixel trails. So apart from it looking a mess, the reason that it's really important to calibrate your images is because the comet, particularly the comet's tail, will only be a fraction brighter than the surrounding sky, especially if there's a lot of light pollution in the sky. So when you contrast stretch your image to reveal the detail in the comet, all you're actually doing is just highlighting all the uneven illumination and all the rubbish in your image. So I use about 40 flats, 40 darks, 40 biases, put them all together and use that to calibrate with, and that seems to give me a reasonable calibration result. Now this actually is an image of 67p. There it is there, and that is exactly the same image, but it has been calibrated. So you can see that the background is reasonably even, and you can actually see some of its tail. So that's why it's worth doing. So all the rubbish disappears like magic. So the last of my 4 consideration areas is image cleanup. And some of the techniques I use I borrow from the Deep Sky Images toolkit. But a word of warning here, it's really easy to get carried away with image manipulation and to introduce an artifact or to misrepresent the original raw data. So here definitely less is better, I think. Now personally, for my comet imaging, I don't believe in things like unsharp masking or deconvolution or in fact any technique that works on part of an image using say a Photoshop layers technique. I think that's gone off the subject of comet science and we've strayed into the world of comet art. But because a bright sky can increase the visibility of noise in an image, I think it's acceptable to use some mild noise reduction techniques, providing you can be sure that it properly represents the original data and doesn't introduce any artifacts. These two pictures started off the same. That one on the right has had some mild noise reduction applied to it. People in the front can probably tell that's a bit smoother, but it is quite subtle. And quite honestly, I think that's all you need to do to your images. Just get some decent data in the first place and calibrate it, and that's all you need to do. So most image processing software has got some form of noise suppression tool in it. I quite like to use Noel Carboni's spaced noise reduction action for Photoshop, but there's plenty of others out there. Now, 4 minutes, right? A bit off-putting seeing that there. Probably the most important thing, or most important cleanup tool anyway, you can use is gradient removal. It's very useful for removing the remaining effects of light pollution that are present in a calibrated image. And as I've already said, light pollution is more intense near the horizon than it is overhead. And of course the moon is a natural source of light pollution, so the sky is always brighter nearer the moon than it is away from the moon. And this causes a gradient across the image which isn't removed by calibration. And when I say gradient, I mean that the image is actually brighter on one side than the other. So on this image you can see that it's brighter in that corner than it is in that corner. And that's because the horizon's down that way and the sky is physically brighter. So if you gradient remove, you get an image that looks like that. It's flat. Now, light gradients in an image don't look pretty, and if they're severe, they will cause some photometry tools to give inaccurate results. So my favourite gradient removal tool is Gradient Exterminator. It's a great name, and it's written by Russell Croman, who's a United States deep sky imager, and he's written it as a Photoshop plugin. But there are others out there. There's one in MaximDL, there's one in PixInsight. You have to pay for those two pieces of software. Photoshop is sort of free. You can download it without paying anything from the official Adobe's website, providing you comply with a few provisos.
Which is that you've got a license. For
well, they don't check up on it. not in my experience, anyway. But also you have to put up with an older version, which is CS2 or older. Anyway, CS2 does everything you need. And I know Nick's a fan of Iris software, which is properly free, and I believe it does everything that you need to do. You need of it. So hopefully that's given you some idea of how I go about my comet imaging from light polluted Southend. And I think far too often us astronomers moan about light pollution, but we don't actually go out and experiment to see what's possible from our particular location. And it's true that a dark site is best, but if you haven't got one, I think that there's still a huge amount of useful comet observing and imaging that can be done, and done well, from a light polluted site. So give it a go. Thank you very much.